So now that we have seen an illustration of how DFS works, I want to actually describe the pseudocode of DFS as well as the running time of it. Okay, for every node, since I want to look at DFS here, for every node, I will have a flag that says if it's visited or not. And in addition, for every node, I will have the timestamp for discovery when it was discovered, the timestamp for finishing when its visiting has been finished, and also I will have a field for the parent. Okay, so the parent will be these parent pointers will actually give us the forest of the trees in this DFS visiting. Okay, so DFS is a recursive algorithm. But remember that if you start from a node and not all other nodes are reachable from that, then if we run the DFS just from that node, then there will be parts of the graph that are not that have not been visited. Therefore, we have to start from a node, visit all the nodes that are reachable from it. Then if there are still nodes that are not reachable, that have not been visited, we need to go visit one of them and run DFS from there. And if there are still nodes that not visited, we have to repeat that, okay? So this is why DFS is written as two functions, the first of which just makes sure that we visit all the nodes in the graph, the second of which is doing the actual work of going from a node to all its descendants. Okay, so the outermost function is DFS, that takes as input a graph G. Okay, so DFS takes as input a graph G, and the first thing it does is it's basically for each node V, it basically marks that visited of V is false. Okay, so the node has not been visited, and it also says that the parent of V, which we usually label here by v.pi, pi for parent, v parent is nil. Okay, so no parents because we have not visited anything yet. And then we have a global variable time that we initialize to 0. This is the time that we are going to use to timestamp nodes for the discovery and finishing time. And now we want to start visiting the nodes. So now we will say that for each node, V, we now need to say if it has not been visited, run DFS on it, okay? If visited V is false, now we need to run the main function that's doing the real work. We call it DFS Visit on this node V. Okay, so this is really what the main function is going to do. The first thing is going to initialize all the nodes to unvisited. The parents of the nodes are nil because there are no parents to them. There is that global variable time, which is the timestamp that we will use to mark the discovery and finishing time of all the nodes. Then we're going to come to every node. If it has not been visited, we will now call DFS on it. Okay, so what is DFS visit of node G and V here? So again, as I said, this is a recursive algorithm, so it's going to look at all the neighbors of the node and call DFS on them. Okay, but since we want to label also the discovery times and all of that, we also need to take care of that and mark things as visited. So the first thing is we increment time. Okay, so remember that in the main function DFS, time was set to 0, so now time is equal to 1, and the first node discovered, it will have discovery time 1. Okay, and the first thing we will do is that we will declare V to be visited. Okay, so V, or visited of V. Actually, since I am using this notation, let me actually, instead of using an array here, sorry about this, let's actually use it as a field, if V dot visited is false, and here if V dot visited equals false, then we do this, okay? So using this, so we say that V is visited now. And when was it visited? It was visited the discovery time. V.D is the discovery time. It was visited at time t, or at time, the variable time, okay? Now we need to call the function recursively on all the neighbors of V. For each neighbor U of V, if U has not been visited, if U visited is false, call DFS recursively on that. But now when we call it recursively, we know that U is being visited from V, so U's parent is V, and now we call DFS visit on U, okay? And once we get out of this here, once we get out of this loop, it means that we have visited all the neighbors U of V. So this is the time when V has been finished. Visiting V and its descendants has been finished here. So now we can declare that V itself is finished, okay? And we can say that we can now increment the time and assign that timestamp now to v.finished, okay, or v.if. Okay, so this is mainly the algorithm here. We basically look at every node. We say that, okay, now once we in DFS visit, we are looking at node V. We declare that, okay, it's been visited because we just saw it here. We assign the time to its discovery. This is the first time we saw it. We visit all its neighbors. Once we are done with all the neighbors, we declare that the node visiting the node has been finished, and we assign that v.f to that new timestamp. Okay, and again the function is recursive. So look at the DFS visit. It's called on all neighbors recursively. This is the DFS algorithm, and if we wanna look at the running time of this algorithm here, if you look at, and suppose the number of nodes is n, the number of edges is m, okay? If you look at this here, at this loop, it's going through every node and initializing these values. This is O of n, okay? The same thing here, but we have to be careful now. What this is going to do, this loop here for each, is going to be iterating on the order of n. I'm not saying that entire loop with all the lines inside it is O of n. I'm saying this loop, in the worst case, it's going to iterate O of n time, because it's going to go through every node. If the node has been visited, it's not going to do anything, but still looked at it, okay? So O of n. And this is really all what's doing the work here, DFS visit. So how long is this going to take? Now, if you remember things from BFS and Comp 182, at that time when I discussed BFS, I said, think about the running time of BFS in terms of the edges in the graph and how many times an edge is visited. And remember that when you have an edge UV in an undirected graph, you can visit V from U and you can visit U from V. So that edge that connects U and V is visited exactly twice. Here in the directed graph, if you have an edge from U to V, that edge is going to be visited once, right? I mean, we are going to look at node V only once. We are going to go from U to V. We don't go back from V to U. We don't visit U from V if the edge is from U to V. So using that reasoning, again, these are all O of 1 here, but using that reasoning, if you look at this here, this is the key issue for each neighbor. For each neighbor, well, then if you look at it, the number of neighbors that are visited equals to the number of edges that are coming out of V, right? And this is going to be applied to every node and all neighbors. So if you look at this here, this is going to work on the order of the degree of V. Okay, this is on the order of the degree of V. So if V has degree 5, we are going, or out degree 5, we are going to be visiting 5 nodes. But of course, this is going now to, on the order of degree of v, times the time it takes to call DFS visit recursively on the neighbors. And this is where we cannot do this in the simple way of just multiplying things. But when we look at this, at the neighbors of V, we say, suppose we have 5 neighbors. We say, okay, now we have 5 operations there. But now we need to look at the time it takes for the neighbors of the neighbors. If you reason about this carefully, these two combined are going to be visiting every edge a constant number of times, okay? In fact, it's going to be looking at the edge from U to V once. Okay, once it's exploring the neighbors of U, it's going to look at the edge from U to V only once. So if we look at this algorithm takes on the order of O of M plus N. Okay, why is the plus N? Because if you look at this loop here, imagine the graph is disconnected, completely disconnected. There are no nodes have any edge, there are no edges in it. M is 0, but still the algorithm is going to take on the order of N time because of these 2 loops here. Okay, these 2 loops are going to take O of N. So this algorithm is O of M plus N. The N is for initializations and going through the nodes to visit them. The O of M comes from the fact that every edge in the graph is visited exactly once. Okay, and this is the same running time as BFS. So there is no, in terms of running time, there is no difference between BFS and DFS. However, in terms of doing other functionalities on the graphs, like checking acyclicity, it's finding strongly connected components and so on for directed graph, DFS is the major underlying algorithm for all these tasks to do on directed graphs. Okay, so now we have illustrated DFS. This is the pseudocode of DFS. The running time is O of M plus N, where M is the number of edges, N is the number of nodes. Next, I will be talking about how to use DFS for doing different functions or doing different tasks on directed graphs.